I think yes, voice is clear. I'm using different systems that's why I'm asking voice is clear. So yes, okay. So we'll start with a different type of knowledge representation. So knowledge representation. So first is FOPL is a first order predicate logic. Just I'm sharing my screen. First order predicate logic. Okay, predicate logic is basically it is one type of a knowledge representation. We can represent the knowledge in the form of a predicate. Okay, so any English language, any language can be converted in the form of a subject and predicate. Okay, any language can be converted in the form of a subject and predicate. Okay, so any fact can be converted in the form of a subject and predicate, and we represent that logic, and that is basically a FOPL, first order predicate logic. Okay, first order predicate logic. In a first order predicate logic, we have a lots of work. So just like any sentence predicate logic, any natural language can be converted into the first order predicate logic. Just like Ram is a man. Okay, so in the predicate logic forms, it will rate means Ram is a man. Okay, is a sentence. Okay, is a declarative sentence. Okay, so here which one is a subject? Subject is a Ram. Okay, and is a man is a predicate. Is a man is a predicate. So we can represent this in the form of a FOPL. You have to retain means we can write is a man Ram. Is a man Ram. Okay, or we can write in this form also, or man Ram. Man Ram. Okay, so just like Ram loves Sita. So this is what a declarative sentence. So this can be written in the form of a predicate logic, just like loves. Okay, loves, and the subject are Ram, Sita. So in a predicate logic, we use different. It has a syntax. Predicate logic. The syntax is, so. This is the example of a predicate logic. Ram is a man. We can write in the form of a man Ram. Ram loves Sita. Loves Ram Sita. So in a predicate logic, we have a different syntax. The syntax of FOPL. So we have a, first of all, in a syntax, we have a set of connectives. We have a set of quantifier. We have a constant. We have a set of variable, and we have a function, and we have a. So in a FOPL, we use a connectives, quantifier, constant, variable, function, and predicate. Okay, so first of all, what is connectives? Okay, what is connective? So connective is basically, so there are 5 there are 5 connectives. Okay, what are the connectives? For example, the connectives are for example, this is a this negation connectives, negation. This is a this is the conjunction. Okay, for a conjunction, basically this is also used. Uh, means conjunction symbol. Another conjunction symbol is a caret symbol, just like this is also used, or ampersand or this. Both are used. This is for a disjunction, and we have a this one arrow means which is a implication, and we have a bidirectional. So these are the connectives. We have a negation, we have a conjunction, we have a disjunction, we have a implication, and we have a bidirectional. Okay. So the next is quantifier. Okay. So next we have a quantifier. Okay. Basically, we have a two type of quantifier. Okay. We have a two type of quantifier. We have a two type of quantifier. One is a universal quantifier and existential quantifier. Okay, we have a two type of quantifier. One is a universal quantifier that is known as a for all x, and uh, another is a existential quantifier. For a universal quantifier is basically it is used with a predicate logic. Okay, for all is a universal quantifier, and for specific we use a existential. Okay, for some of them that is a existential. Okay, so just then swing you the symbol. Yes. So universal quantifier. There is a two type of quantifier. One is a universal quantifier, and another is existential quantifier. So universal quantifier, it is used to define for all FOL for all object that is represented by a upside down capital A. Okay, basically this is for all A. This is for all A. Okay, this is for all A. So this is known as a universal quantifier. This is known as a universal quantifier. So this is universal quantifier. Okay, for example, for all X, man X, drink X coffee. Okay, so there is a natural language. There is a all man X. X is a there man who drinks coffee. Okay, for example, all man drinks coffee. For example, if the uh, natural language is all man drink coffee. So that means all men. So we can, all man means we can represent using for all x. For all x. This is the symbol for all. Okay, x is basically a variable. X is a variable. So for all x, man x means x is a man. For all x, man x. Drink is a function. X drinks, that is a coffee. So x drinks coffee. So drink is a function. Drink is a function. Okay, so x is basically the name of the person. Okay, so x is basically, here is a, x is a man. So x drinks coffee. So there are all x where x is a man who drinks coffee. There is all x where x is a man who drinks coffee. Okay, so this is known as a universal quantifier. This is known as a universal quantifier. Okay, the next is existential quantifier. So existential quantifier is basically, it is universal quantifier means basically it is based on all value. Okay, and existential quantifier is basically sum of them. This is basically a sum of them. It is used to define for all to some object, not for all, for some object, specific object. Okay, some specific object is a sum object. So that is represented by a backward capital E. Okay, this symbol is used for a existential operator. Okay, just like some boys are intelligent, some boys are intelligent. Okay, all boys are not intelligent, some boys are intelligent. So sum of x, boys x means x is a boys, sum of x, x is a boys, and x is a intelligent. So we represent in the form of a FOPL, sum of x, x is a boy and x is intelligent. Okay, so there is some x where x is a boy and who is intelligent, and that is known as a existential quantifier. So we understood we have a two quantifier. One is a universal quantifier, that is a for all x, and the existential quantifier, that is what a sum of x. So the next is constant. Okay, so the next is constant. Constant means basically, what is constant? Constant is basically a some fixed value is a constant value. Okay, some fixed value is a constant value. So constant is also a quantifier. Maybe some specific value is a constant value. Okay, some specific value is a constant value. So that constant value is referred to some specific values. So constant means basically a fixed value item that is belongs to a domain. Okay, just a minute. So constant. Okay, so we are dealing with a constant value. Just a minute. See, constant. Constant means what we can say. Constant. So constant are the fixed value terms. Okay, that belongs to a, just a minute. हाँ हेलो क्या जल्दी बोलिए हम मीटिंग में है इम्पोर्टेंट है बाद में फोन कीजिए ना, अभी एक्चुअली अभी मीटिंग में है, ठीक है। Yes. Yes, and yeah, constant are the fixed value belongings to a given domain of discourse. So constant is basically a specific value. Okay. For example, instead of x value, if we want to specify a specific value, okay. So that basically just like here for see, drinks is a function. Drinks is a function which having a two parameter. Drink is a function which having a two parameter is a x and y. Okay, x is the name of the person and y is a means x is the name of the person, y is the name of the drink. Okay, so here instead of y we are specifying coffee. Okay, so that is basically the constant value. Means man drinks coffee. Okay, so this value is a constant value. So the next is variable. So variable is basically we use various variable for various operation. For example, like for all x, for all y, for all z. That means we are using three variable. Okay, and we are performing different operation. So this is x, y, z is a variable. Okay, variable is basically variable means basically just like a for all x, for all y, and for all z. Okay, this x, y, z are three different variable. And next is predicate. So what is predicate? Okay, in predicate logic, this is the important predicate. So predicate symbols predicates define on domain D. Okay, for example, just like we define a predicate like income. Income, uh, we have defined an income tax. Okay, x and y. So we define a, for example, we are calculating an income tax. Okay, we define some predicate. For example, we are defining some predicate like a merit. Okay, just like we have defined so we define a predicate just like a for all x, for all y, man of x means x is a man, and woman y is a woman, implies to married xy. So this married is a predicate. Okay, married is a predicate. Man and woman is also a predicate. Man and woman, that is also a predicate. So here we can write a predicate means basically married is a predicate. Okay, so x is a person, Y is also person, X is a which type of person? Is a gender of men, Y is a woman, and implies to X married to Y. X married to Y. So this is what a one FOPL, first order predicate logic. Okay, using this is what a simple theory of a predicate logic, FOPL. Okay, next I'm explaining uh, how to implement means FOPL. So there is a natural language like all employee all employees earning dollar 1400 or more per year pay. So this is a question. So from this question, we'll assume this is a natural language. All employee earning 1400 or more pay taxes. All employee earning 1400 or more pay taxes. Okay, so this is a natural language. So we need to convert this natural language in the form of a FOPL. Just so this is the natural language. So how to write the FOPL for this? Okay, how to write the FOPL for this? So so for that, all employee. So that means you have to write for all for all. We are writing EX. So we assume EX means employee X. For all EX, for all EX, or for all X EX, and earning 1400 or more. Okay, GE, we have defined a predicate. Okay, GE IX means IX means the income of X. Okay, if it is more than $1400, if it is more than $1400. Okay, so then T X. Okay, so we can write EX. X is an employee. Okay, GE is basically GE is basically a income, basically a XY income of X is income of X is greater than y, and tx uh, pay tax x pay tax. So this is a its explanation of this. So this is what FOPL. I hope it is clear. One explanation. This is one FOPL statement. So another one with a more. Some employee are sick today. So this is what a natural language. Some employee are sick today. So that means all employee are not sick. All employee are not sick. Some of the employee are sick. Some of the employee are sick. All employee are not sick. Okay. So we can write sum of y e y. Y is an employee. Okay. Y is an employee and s y. Y is a sick. Okay, y is an employee and y is a sick. So that is what are not all employees, some employee. Okay, so ey means y is an employee where e of y is an employee and s of y is sick. Okay, so this is what some of employee are sick today. One more example. No employee earned more than the president. No employee earn more than the president. Okay, so here also you have to take a universal quantifier. Okay, no employee means you have to check with the all employee. Okay, and you may use a negation also. Okay, so for all x, for all y, for all x, for all y, e is a E of x means E is an employee and you may use this as an and y is a president. Okay, so not GE greater than equal to I of x and I of y. Okay, so here where just need the explanation where e of x means is x is an employee, x is an employee, and p of y, that is y is a president. Okay, and I of x or I of y, whatever it is income of x, and GE greater than x to y. So this is what a no employee earned than the president. No employee earned more than the president. I hope some of the concept is clear, how we can use a universal quantifier, how we can use a existential quantifier. I'm giving some more example. Uh, it, uh, so it is. So the first query is, the natural language is some patient like all doctors. Okay, some patient like all doctor. Okay, so here sum of x, sum of x, px, x is a patient, and for all dy, y is a doctor, implies to like xy. X means is a patient, y means is a doctor. Okay, some patient like doctor. Okay, so sum of x, and for all y dy like xy. X is a patient, y is a doctor. So we are using universal quantifier for the doctor. We use a existential quantifier for the patient. The next, no patient like any qua. So for all x, px, so p is a means x is a patient, and for all y, key y quick, not like x and y. So x is a patient, no patient, like quick. Everyone who saves money earn interest. Everyone who saves money earn interest. Okay, so uh, for all x, saves money is a predicate. X means x saves money, implies to earn interest. X earn interest. For all x saves money, x saves money, and x earn interest. Next, if there is no interest, then nobody save the money. If there is no interest, nobody save the money. So sum of x, not interest x. Okay, that means there is a x does not pay the interest. Okay, implies to not save money x. Basically, this sentence is fully a negation sentence. If there is no interest, then nobody saves the money. Means save money is also negations, and interest is also negations. Okay, so sum of x, x does not take an interest, that means x does not save the money. The next, yes, all employee earning 1400 or more pay tax. Already I have discussed this one. Okay, for X, EMPX greater than G, income of X 1400, tax this. No employee sick today. Okay, it is something different for all X, not EMPX. Sick on X today. So that means no employee on sick today. Means all employee are working fine. Okay, so no employee is sick today. So no employee earn more than the president. No employee earn more than the president. For all X, for all X, for all Y, for all X, for all Y, EMP X is an employee, president Y is a president, implies to not greater than equal to income of X and income of Y. Means income of X cannot be greater than income of Y. So that means no employee earn then more than the president. Or hated him. Everyone is loyal to someone. People try to assassinate ruler as they are not to. Mark tried to assassinate Caesar. In okay, I've told the logic how to use the FOPL, how to one complete FOPL. Okay, set of questions. One question from FOPL will be there. So this is a sample. So next, how to convert it? Okay, Marcus was a man. Marcus was a man. First, try to write in your try to form. I'll explain. Okay, first try to you okay identify which one subject and which one predicate. Marcus was a Pompey. Existential quantifier. Caesar was here. Subject and which one is a predicate or hated. So all means not be a, you have to use a universal quantity, become a universal quantifier. So it become a existential quantifier. People try to associate, just use predicate here. Marcus tried to assassinate Caesar. Giving 2 minutes, just try to write in your copy. Then I'll solve. Question. And, few example. And basically, I have taken often this question from one of the famous book is artificial intelligence. Yeah. Starting with first, Marcus was a man. We can man Marcus. We can write man. Next, second question. Marcus was a Pompeian. Marcus was a All Pompeian were Roman. All Pompeian were Roman. Okay, so for all x, Pompeian x implies x. For all x, Pompeian x, all Pompeian okay, so anywhere all will be there. So that means it will be a universal quantifier. Next, Caesar was a ruler. So subject is obviously is a Caesar, and was a ruler is a predicate. So we write a Caesar, ruler, Caesar. Next, all Roman either loyal to Caesar or hated him. Loyal to Caesar or hated different quantity. Okay, okay. So X is a loyal to Caesar. So all Roman for all X, Roman X, all are Roman. That is a Roman X. Okay, either loyal to Caesar. So X Caesar, X Roman who is loyal to X, all Roman, and this is a operator is a or operator. This is a or operator. Or hate we use a predicate. If the constant value is the is a loyal to Caesar or hated the Caesar. Either loyal to Caesar or means we use the next. Next is someone. Someone. So everyone means obviously there will be a some universal quantifier. Okay, everyone means basically it will be a universal quantifier. Okay. Okay, implies to y. Okay, loyal to x comma y means x is loyal to y. So that is what everyone is loyal to someone means x is so x is loyal to so everyone someone. The next X means the ruler one which prolong. Okay, is a why which way it represent using object. Okay, in the form of a frame. Okay, in the form of a frame. So it represents fully in the form of a frame. So frame was first introduced by Marvin Minsky, okay, as a data structure to represent the mental model of a stereotypical situation such as a driving a car, attending a meeting, eating a restaurant. Okay, so it is represent in the form of a means some situation. Okay, so that any it will represent in the form of a object oriented. Okay, in the form of a object oriented. So we have defined the frame name of the frame, slot one. So it is divided into set of any frame consists of a collection of attribute. Okay, frame means basically the name of the object, and within the frame there is a collection of attribute. Okay, so the attribute is divided into a again known as a slot. Okay, and every slot is divided into a multiple facet value. Okay, so frame name slot 1 facet 1 value 1 facet 2 value 2. Okay, similarly slot 2 facet 1 value 1 facet 2 value 2. So this is a syntax. This is a syntax. So this is a syntax for representation of a frame. Okay, so in a frame based system basically we write any situation. Okay, so it is represented into a object oriented. So that means first of all one object will be there. Within object we have lots of properties of object. Okay, which is known as the characteristics of the object. We define that as a slot. Okay, any object having a lots of slot value. Slot value is basically the properties of the object, and one property can also divide into a small sub property. Okay, so frame name slot 1 facet 1 value 1, facet 2 value 2, facet 3 value 3, slot 2 facet 1 value 1, facet 2 value 2. So this is what a syntax. See, so we assume we are representing by a person. The person name is a Bob. Okay, so Bob is the name of the frame. Okay, so in a frame-based system, the most important thing is basically the parenthesis. Okay, as given. Okay, opening parenthesis and closing parenthesis should be proper. Okay, opening parenthesis and closing parenthesis to be proper.